After having derived Cauchy's integral theorem, we now take up some these problems based on that theorem. For example, let us consider a simple integral. Integral I is equal to that loop integral along a curve C dz divided by say z square minus 5z plus 6. We have to integrate it, as I told you in my last lecture. The question is incomplete yet. We have to specify, we have to integrate along which curve. The curve C is a unit. The question says that the curve C is a unit circle centered at 0 origin. That means if you have this as the complex plane and you have say 1 here, this one, this is 2 and minus 1, minus 2, the path, this C is a path that is a circular path which is centered at, say, it is given that this z is equal to, say, it is in the question that we are given that z is equal to 1 units, that is circle, the radius of the circle is 1, radius of the circle is 1. Okay, it is this circle, this is the path, this is our path, circular path. The path is simple, and then we have to integrate over this path in counterclockwise direction, in this direction. Okay, now let's see one thing, let's look at one thing, that is, if we examine this integral, we find that it has its denominator is that can be written as z minus z square minus 2z minus 3z 2z, that is 5z plus 6, and then it can be split into these factors. Partial fractions are that you should be familiar with partial fractions for handling problems in complex integration. Partial fractions often are required, so we don't require it here. It is quite simple. Dz is equal to, we can take z as common, we have z minus 2 then minus z minus 3 z minus 2 z minus 2. So we have dz integral dz divided by z minus 2 common into z minus 3. That is our this integral. I have converted this to this because I want to show you something. That is, look at this function. Our function here is, if I write it here, fz, sorry, our function here is 1 by z minus 2 into z minus 3. This is our function fz. Now if you look at this, you see that at z equal to 2, the function blows up. You see, put z equal to 2 and the function blows up, and z equal to 3 function blows up. We say that this function has singularities at 2 points, z equal to 2 and z equal to 3, z equal to 2 and z equal to 3, z equal to 3. So at this point, z equal to 2 point, and at this point it has singularities. I will show these singularities by crosses, as if these are dangerous points. Now, fortunately, the path given to us in the question avoids these singularities. Singularities lie outside this. There are no more singularities in this function. Hence, we are sure, we are confident, we have every possible proof that the function is now analytical on this as well as inside, because we have avoided singularities. The path is such that we have avoided singularities. Since the function does not contain singularities, now you need not even integrate it. You just write 0. Write 0 because you are sure that the line loop integral of this will be 0, because there are no singularities inside this or on this. That is how complex integration goes. I think it is even simpler than real integration. Let us go to another page. Now another, for example, similarly we can have another this function, something like this. Say I have integral given, which is integral c 3z square plus 7z plus 1 divided by z plus 1 dz. Now again in this, if you look at the function f z, z is equal to minus 1, the function blows up. And if this curve encloses this point, so this point lies inside the curve, or on it is supposed the curve is this complex plane, and the curve is, say, suppose, and minus 1 is here. This minus 1 z is equal minus 1 is here. Since minus 1 lies within the curve, the singularity lies within the curve, the value of this integral along this curve will not be 0. It will not be 0. However, we are given that that this curve is a circle of radius 1 by 2. Circle of radius 1 by 2. So if it is a circle of radius 1 by 2, sorry, I'm sorry, but I'm showing this minus 1. I'm sorry. I beg your pardon for this. It is minus 1 on this side. Circle has a radius 1 by 2. This means 1 by 2 is here. 1 by 2 minus 1 by 2 here, and then the circle is like this. The path of the integration avoids this singularity. When the path of the integration avoids singularity, then you can easily say that this integral is equal to 0. So these two were actually warm-ups for us. And now let us go to another very interesting and very important thing, that is path independence of complex integral. Path independence. You know, in physics, this concept is so important that many things in physics are hinged on this concept. Now, path independence. Suppose we have this again a complex plane, and then we have a function which is whose domain is this, is defined in this, and then there inside it there is a path, a closed path. This is closed path C. Call it, say, C1. Let me call it C1. This closed path. This closed path, there are 2 points A and B on the closed path. The function fz, we have a function fz which is analytical on this, at every point on this, and analytic on inside this, that means on these points. So if it is so that it is analytical on the path as well as inside it, then function fz we can say it is integral, loop integral over this path is equal to 0. Over the path C1, I have called it C1. I will tell you why I am calling it C1. Now, or C, let us first keep it C. Let us write it C. Okay. Now, that is good. Now, I can write this integral along this closed path as 2 integrals. One, I will divide this path into 2 parts. One from this A to B on the upper side, from upper side A to B, I will call that part of the path as C1. And from B to A, I will call that path C2. So I can write, instead of this C, I can, the original path was C, and C has been divided into 2 parts, C1 plus C2. C1 that goes from A to B along this arrow, and from C2 that goes from B to A along this arrow. Now I can then break this integral into 2 parts. C fz is equal to, that will be equal to C1 fz dz plus C2 fz dz. Now repeat this. Now we are going to do something with this path C2. Suppose I consider another path that is identical to C2, identical, but traversed in the opposite sense. That is this path. Not exactly this path. This actually the path that I am speaking about is coincident with it. It is everywhere falling on C2. The two paths are coincident. It is just for this visualization that I have shown it a little bit away from C2, but otherwise I am actually talking of the C2 path but in the reverse direction. Such a path is called, we write that, minus C2, for the obvious reason, minus C2. So if I take this minus C2 path minus, I can here write that I can here in place of this C2, I can write minus C2 for that, minus C2 for this, and then the integral will become, integral is, I have, once again I go back to this, I show these two paths. One is, say, suppose C1 that goes from A to B, then that was C1, and then C2 from B to A, C2, and we had C1 plus C2 fz dz equal to 0. Now what I am going to do, I can first of all, let me do one more thing, that is I can break this total integral into two, that is fz dz along C1 plus fz dz along C2. Note that I have not put this circle, little circle on this, because individually the paths are not closed. Each path individually taken alone is not closed. It is the whole that is closed, and then it is equal to 0. Now I can do one thing, that is I can transfer this to that side. I have C1 fz is equal to sorry, it is plus here, so it is equal to dz, that is equal to minus C2 fz dz. If this path is now traversed in opposite direction, say you are traversing a path first in this direction, then opposite direction, the two integrals will be minus of each other. Why minus of each other? Because in one if you go from this to this, in one you are traversing this path in anti-clockwise direction, and in the other you are traversing it in clockwise direction. As we have already said that we will always adopt this anti-clockwise direction as our normal direction, then this clockwise direction definitely is negative. Or you can also understand it like this: you have a path like this, and if you are going in anti-clockwise direction, you are taking its elements, say each element delta z in this direction, delta z points in this direction, delta z points in this direction. But when you are coming back, each delta z is pointing in the opposite direction. It's pointing in the opposite direction. So this integral will be negative of this integral. Keep this negative here, and then I will write inside minus C2. Minus C2 means in the opposite direction, fz dz. Okay, then minus will become plus. I will write this here. Minus will become plus, and I will have then integral in sorry. Oh God, or should I undo this? Yes, it has to be undone here. Just a minute. Okay, let us do it here. We have our first integral was, that was fz dz along path C1, along C1, this, and now we found that this is equal to minus plus, that is equal to plus minus C2 fz dz. If I call this minus C2 as by some other name, say I will call it by name, say C3 name, then I simply have discovered an interesting thing, that is C1 fz dz is equal to that is equal to C3 C3 no, this is not close, sorry, this is C3, it is C3 here, C1 C3 fz dz. Let's look at what we have actually derived. What we have got? We have got this thing, that this is C1 and this is C3. The minus C2 is what I called C3. This is C3. Both paths C1 and C3, they have the same starting point, which is A. They have the same end point, which is B. They go from A to B. They both go from A to B. Okay, but see, their integrals, none of them is closed, each one is open, and their integrals along these two different paths, along C1 and along C3, they turn out to be equal. It means that it does not matter which path you choose for integrating a complex function from one point to another point. It does not matter which path you choose. That means this integral fz dz is path independent. It does not depend upon path independent. Sorry, don't put this there. Path independent. It is path independent. Okay, now that we have established that it is path independent, we have some these consequences of this. Number one, you have established that this path, say C1, and another path, say C2, A, B. You establish that integral along this path and integral along this path, they are equal. Now, if they are equal, this means that we can then deform one path into another path. You can, for example, deform C1 into C2. Deforming means you, instead of C1, you can take, say, C2. Somewhere it may be very useful to replace one path with another path. Another path may be simpler than the first path. So you can do it without changing the integral, provided, of course, your integral should obey Cauchy integral theorem, these properties, requirements. That is good. Now, this is not only true for these open paths, that you can replace one path by another path. It is also true for these closed paths. For example, let's take this case, an interesting case here. Let's take it. We have a closed path, say, let this be a closed path, let us call it C1, traversed in this direction, in this way. You can see which way it is anti-clockwise. And another closed path within it, contained completely within it, that is C2. C2 again traversed in this anti-clockwise direction. Okay. Now, C1 and C2. Suppose what I do, I choose 2 points on these two. One is, say, A here, or B here, and A here. Okay. And then what I do, I break these here, and then first keep this diagram below, because it will help you what actually they were at the start. And let us make a fresh diagram here. Okay. Or C, this is C2, this is C1. Okay. Now one point is B here, and A here. What I'm going to do, I will cut this path and this path here, and then connect A and B like this. I will connect them like this. Say I will take this this like this and like this, and in between I will it will be like this. The final shape will be like this. For example, let me show you that final shape first. This will be like this, and here at this place I will put a cut in it. This is the cut at A, and then this is B here, and then I have this C2. C2 path here. This was the C2 path. This is that C2 path. C2. This was C1, our external path. This is A and this is B here. B here. Now what you do is this. You imagine this A and these two sections to be close enough. Of course, they're close so that we can call this opening here A and this opening here B. Now, imagine this thing. Now, you have added a new path, some segments of a new path. Say one is this. Let me show it. It comes like this here, and then it goes like this. If it goes like this, then it will go like, but this goes against it. This goes in a direction that is opposite to it. So I will do this thing. I will uh, I am actually, I will do this thing. I will show it like this. C1 coming here, and then coming here, and I will now reverse this direction of C2. See, it will be minus C2 now. Minus C, instead of C2, I will take minus C2. Minus C2 in this direction. So that it becomes continuous. You see it. You see it here. And then it leaves like this and goes like this. Everything is now harmonious. Now, what we are going to do, we have C now broken down C into four pieces. Yes, one is C1, another is C2, the third one is C1. Okay, another is C2, C dash. We should call that C dash. That is the, I want to show you this C dash. This segment I am going to call C dash, and this opposite segment will be called minus C dash. So it is C1. So let us go for with this C1 up to this, then C dash plus C dash. Then after C dash, what we have? After C dash, we have then minus C2 plus minus C2. Lastly, I have plus this minus C2 minus plus minus C dash is equal to 0. Here was our original. This was our original situation. C1, C2. This is here. Okay. That is sorry. This is the total path available with us. Now we know that integral of this our integral, say integral fz dz along this path C can be split into four integrals. Integral C1 fz dz plus integral C dash fz dz. None of the individual integrals is closed, so this is wrong to write it like this. Plus then you have integral minus C2 fz dz plus integral minus C dash fz dz. Now you have this last look at this whole has to be 0. Why? Because this whole has to be 0 because these paths, all the paths are smooth. They are smooth. The function is analytical on them, on all the paths, and in between them the function is completely analytical. And that means this path C made up of these pieces. Since this path is complete, this path, for example, it starts from this. So let you start it from this. It starts from this, goes into this, then goes here, then goes here, then comes again. See, it does not intersect with itself. That means it's simply connected. So we have this function fulfilling all the conditions of Cauchy's integral theorem. Hence, it is integral that will be 0. Now integral is 0. Now what else then? you see that you have now check this integral. Check this fz dz. First of all, these two integrals. this integral and this integral. They are, since they are traversed in opposite directions, hence this integral, I mean integral this c dash, this integral, and minus c dash, these two cancel out, they are gone. Okay, then you are left with this integral fz1 c1 yes, is equal to dz is equal to fz dz c1 is equal to just a minute, integral this integral c1 fz dz is equal to integral c2 because when you transfer this to that other side, when this goes to this side, it becomes minus here, but then reversing the orientation of the curve, reversing that will leave another minus. The two minus will cancel out. Once more, you can, when you take this to this side, it becomes minus integral minus c2 fz dz, and now reverse this c minus c2, make it c2, again a minus, this minus and that minus, those will cancel, and you get c2 fz dz. What has this shown to you? It has shown to you that you can leave this path, you can do away with this path, and instead of this you can choose this. The condition is that the function should be analytic on this path, in between them. Now if you can further deform this path into, say, another path, provided the function should satisfy those conditions which I am talking about, that which are dictated by Cauchy's integral theorem. Yes, then you can even squeeze it into smaller path, then even smaller, leading to the point. This is a result that we will use. So let us go to a very interesting, very important integral. We call that little integral. We call that, its name is important little integral. What is it? Important little integral. Let us see what is it. What is the important little integral? It's an integral, this integral, again a closed loop integral, z minus a raised to n dz, where n is an integer. It can be positive, it can be negative, it can be zero. This integral is very, very common for n negative n. For example, if n is equal to -2, suppose n is equal to -2, then this integral will be of this shape, of this form, integral c1 by z minus a raised to 2, -2 power is n is -2 dz. Integrals of this type, we will be actually experiencing, encountering those integrals, and let's see, can we integrate it. But we have first say integrate it where say a curve. So C is any curve. Let's take here any curve, guaranteed. But we guarantee you one thing, that this curve is piecewise continuous, smooth. That means smooth, piecewise. And there's one more thing, that is this curve lies in the domain of this function. The function is analytic on this curve and in the region inside the curve. So suppose we have this region, this region, any curve. Now the function should be just this is the curve. Say, let me say, call this curve C. Function should be that should be analytic on every point of this curve and inside this. Then I want to integrate it along this curve. I will along this curve, where yes, z is, what is a? A is a point in this region, in this region D. Say Z is A is here. Since A is a point in the complex plane, hence A is a complex number. Don't think that A is something a real. It is complex number. That is very important. That is very important for a solution of this. A is a complex number. Now, you know that if this A, if n is negative, suppose n is minus, then at A it will have singularity. Yeah, definitely, because you can see, suppose n is equal to -1, the function will be z minus a raised to 1, and when z is equal to a, the function blows up. So it has a singularity. Then we will at the beginning we will let n be both positive, negative, and 0, all these, and we will handle these cases differently. Let us now we have to integrate along this path. But what I will do, I will not integrate along this path. I will take a circular path of some radius, say r, small r. Radius of the circular path be r, and I will deform this path C into this circle. You can do that because the function is analytic on this point, on this function is analytic on this path, and function is analytic in between. Of course, function is not analytic here at A, but that point is not in between these two. As long as that point is not in between these two, you can deform C into this. No problem in that. Now we have now let's begin now. After deforming this, let us do one thing. We use a substitution. We put let z minus a be equal to r e raised to I theta, or e raised to I theta. What is it? Z minus a, z is a complex number, a is a complex number. Difference of these complex numbers is a complex number. That complex number I have written as r e raised to I theta. I can do that because you know that r e raised to I theta is equal to cos theta plus I sin theta multiplied by, of course, by r. That gives us real part, this imaginary part, this is the imaginary part, that is the real part, and then we have now this r sin theta. Okay, now so with this substitution, what we need one more thing, that is we need this del z. Del z will be equal to if you differentiate it with respect to theta, r is constant. You are actually using a circle of constant radius. R is constant, so you have r I e raised to I theta. Theta is changing. Theta, that means at this angle. See, this theta is basically this angle. It is changing as this you move the angle theta on every point on the circle is changing. Anyhow, we have then d theta. Substituting this there, then we have I is equal to integral z minus a, that is z minus a or e raised to I theta raised to n, z minus a raised to n, okay, into dz, that is r I e raised to I theta d theta. We can take constants outside. R raised to n leaves here, this r raised to 1 leaves this, r raised to n plus 1 we have then, and I2 is constant, so bring it here, and you have e raised to I theta, e raised to n theta, it is e raised to n I theta plus this theta, I theta d theta. Once more, e raised to, okay, you can do it yourself, that's quite easy. I r raised to n plus 1, then you have integral e raised to n, I should take theta out, I theta out, and then n plus 1 d theta. Proceeding further, we have then I r raised to n plus 1, and when we integrate this, you know, that will be e I theta n plus 1 divided by I n plus 1 divided by I n plus 1. I will go, and then we are left with this much. We are left with, say, we now turn to another page. We have reached this stage where, let's go back once more. We go back to this. I is equal to r raised to n plus 1. I is equal to r raised to n plus 1 divided by, then once more, r is e raised to theta n plus 1, e raised to theta into n plus 1 I theta, perhaps, yes, I theta n plus 1 divided by, divide is that there, n plus 1, yes, n plus 1 divided by n plus 1. So this is our integral, I e raised to I theta n plus 1. Okay, now, but I'm sorry, I have not used limits. I'm sorry. This is a definite integral. As you move from, say, this point to this point, theta changes from 0. It changes from 0 to 2 pi. I'm sorry for this, 0 to 2 pi. So I have limits 0 to 2 pi. Now I have this here, 0 to 2 pi. And when I substitute them, there I get I is equal to r raised to n plus 1 divided by n plus 1. That's okay. Then I have e raised to I theta in place of theta 2 pi n plus 1, 2 pi n plus 1 minus e raised to 0, this 0, that is 1. Now, if you expand it by using Euler's formula, you have r n plus 1 divided by n plus 1, or n plus 1, and then you have cos 2 pi n plus 1. I am using Euler's formula, minus plus I sine 2 pi n plus 1 minus 1. This one. E raised to 0 is 1. Okay. Now, you know that this, after all, is an integer. N plus 1 is an integer. 2 pi multiplied by integer, and then if this 2 pi is fed to cos, it produces 1. For example, cos 2 pi, that means cos 260 degree, 360 degree, that is 1. Cos 4 pi, that is 1, and so on. Now this is 1. This is 1. Okay. This will be 0 because sine 2 pi and sine 4 pi, those are 0. This is 0. This is minus 1. Minus 1. So this whole becomes 0, and this then becomes 0. So this is 0 provided this becomes 0 provided n is not equal to minus 1. Look, suppose n is equal to minus 1, then it will be indeterminate, because numerator becomes 0, denominator will become 0, 0 by 0, it will be indeterminate. So for n not equal to minus 1, this integral vanishes. You need not bother about this integral if n is not minus 1. If n is not minus 1. For example, in our previous example, I had shown you this. I had shown you, say, for example, perhaps I did show it. I don't remember exactly whether I showed it that or not. Not actually. Now let's go back. Going back, and when I talked about this integral, and I said n is equal to, for example, minus 2. If it is minus 2, then this integral is destined to be 0. It is written in its destiny that you will be 0. Now, the case of n is equal to minus 1, that's a curious case. We need to handle that separately. How can we treat that separately? Let's go back to this stage. We should not yet carry out the integration. Sorry. Let us go back to this stage when we had not carried out integration. This stage. At this stage, we are going to do something. That is, let's see. I is equal to back to this I or n plus 1. I or n plus 1, then I or n plus 1 integral integral 0 to 2 pi, integral 0 to 2 pi e raised to I theta n plus 1, e raised to I theta n plus 1 into d theta. Of course there will be d theta here, d theta. Okay, so this is what we are actually before integrating it, we had this thing. Now put n equal to 0, n equal to -1, put n equal to -1 in this, we get I is equal to I or n is equal to -1, this will become 0. Okay, this becomes 0, or n is -1, and then when we go to the integral 0 to 2 pi without carrying out integration, e raised to n is equal to -1, this will become 0 d theta. That is, if I now go to this, for example, I let me clear here some space for the final result. I have I is equal to I, okay, I or raised to 0, that is 1, then integral 0 to 2 pi, then e raised to 0, that is 1, into d theta, e raised to 0 is 1. Now that is a simple integral. It is equal to I into d theta, that is 2 pi, that is theta, and these are 0 to 2 pi. So it is, our final answer is for n equal to -1, this integral is equal to I into 2 pi minus 0, that's 2 pi. Simply the value of the integral is 2 pi I. So we have the final result. This integral, this very interesting integral, z minus a raised to n dz, this is along a curve, of course a closed curve, that is along any piecewise curve. You know what we did, we actually choose, because we can deform curves, so we choose that simple curve. This is equal to, this will be equal to n plus 1. Sorry, this has two values. Number 1, 0 if n is not equal to -1, 2 pi I if n is equal to -1. That is this. Please remember this integral. It is known as, we call it little important integral, or important little integral. Let's call it little integral. It will be very important for us for establishing this Cauchy's integral theorem, integral formula. Okay, thank you.